Hello everyone, very good evening to all of you. Good evening everyone, good evening. Am I audible, visible? Please type in a chat box. Am I audible and visible? Shall we start today's session? Shall we start today's session? Okay. So I think video and audio both are clear. Okay, so let's start today's session with this question. Right, let's start today's session with this question. Okay, so in this question, there are two blocks, block A and block B. Right? In this question, if you see there are two blocks, block A and block B. Block A having mass capital M and block B having mass small m. Right? And both the blocks are connected with the help of a string. So this is the string. Right? This is the string. Right? And there is a frictionless pulley. So arrangement is like this. Right? There is a frictionless pulley and block A and block B is connected via this frictionless pulley with the help of a string. And there is a plane, and to reduce the friction between plane and the block, right, to reduce the friction between the plane and the block, there is a lubricant, and lubricant having viscosity, that is mu. Right, lubricant having viscosity, that is mu. So what is my question? What is my question? Question is find the terminal velocity. Find the terminal velocity of block A. Find the terminal velocity of block A. This is the question. Right? This is the question. Okay, so if you draw the free body diagram of block A, right? If you draw the free body diagram of block A, so see, this is the block A, right? This is the block A. This is the block A, right? And there is a tension, right? So this is the tension in a string, right? Let us consider the tension is T. Let us consider the tension is T. And this block is trying to move in this direction with terminal velocity, that is Vt. Right? Block A is trying to move in a positive x direction with terminal velocity Vt. So if I ask you what is the direction of shear force, so can anyone tell me what is the direction of shear force? Can anyone tell me what is the direction of shear force? So obviously, direction of shear force is in the negative x direction, right? And block A having mass capital M, so what is the weight? So we can write capital M multiplied by G. So this is the weight of the block A, right? Now if you write the equation of motion, for block A, so simply we can write summation Fx is equal to max, right? This is the equation of motion for the block A. Now what is the acceleration? Because here we are talking about the terminal velocity, and what is the terminal velocity? The terminal velocity is the steady state velocity, right? Terminal velocity is a steady state velocity. So acceleration is 0. Acceleration is 0. So simply we can write summation Fx is equal to 0. Summation Fx is equal to 0, right? And we can write minus Fs. So Fs is in the negative x direction. So minus Fs plus T, that is equal to 0. So simply we can write Fs is equal to T, right? Fs is equal to T, right? Now, can we calculate this T? Can we calculate this T? Can we calculate this tension in a string? So yes, definitely we can definitely we can calculate tension in a string, right? Now see, in here the tension is T, and since pulley is a frictionless, therefore here also the tension is T, right? If pulley is a frictionless pulley, then we can say whatever the tension experienced by this string, the same tension is experienced by this string. So tension is same because pulley is frictionless pulley, right? Now see, if you draw the free body diagram of block B, if you draw the free body diagram of block B, so this is the block B, this is the block B, and block B having mass small m, so what is the weight? That weight is m multiplied by g, right? And what is the tension in string? So tension in string, that is T. So this is the free body diagram, this is the free body diagram of block B, right? And if you write the equation of motion here, so in a y direction, summation Fy is equal to m ay, right? Summation Fy is equal to m ay, and since we are talking about the terminal velocity, so acceleration is 0. Here also that acceleration is 0. So simply we can write summation Fy is equal to 0. So simply we can write T is equal to m multiplied by g. The T is equal to m multiplied by g, right? So this block having a small this block having mass small m, and this block having mass which is capital M. So what is the tension? The tension is equal to m into g, right? Small m multiplied by g. So simply we can write that Fs is equal to, this is m multiplied by g. Fine. Now can we find out the shear force from the concept of fluid mechanics? So this is the engineering mechanics concept. So can we find out the shear force? With the help of fluid mechanics concept? So yes, we can find out. We know about Newton's law of viscosity. So from Newton's law of viscosity, right? The shear stress is equal to, or shear stress at any layer is equal to mu du by dy at that layer, right? Now if you see block A, right? Block A is in contact with the liquid, right? Or you can say lubricant having dynamic viscosity mu. Can we find out du by dy? Can we find du by dy? Not possible, right? Why it is not possible? Because velocity variation in this lubricant is not mentioned in the problem, right? Without knowing the velocity variation in this particular lubricant, it is not possible to calculate the shear stress, right? So if velocity profile is not mentioned, then what is the velocity profile we assume? What is the velocity profile that we assume if velocity profile is not mentioned? I already told you multiple times, if velocity profile is not mentioned in the problem, right, then consider as a linear, velocity profile, right? Yes, absolutely correct, right? So assume linear velocity profile. Assume linear velocity profile. So linear velocity profile, now exaggerate this particular portion, zoom this particular portion. So if you zoom this particular portion, then see, this is your fixed plane, right? This is your fixed plane, see, this is your fixed plane, right? This is the fixed plane, and above the fixed plane there is a lubricant. So this is the lubricant, right? This is the lubricant. And if you see the velocity profile, so this is the velocity profile, right? If you see the velocity profile, then this is the velocity profile, right? A layer which is in contact with the block having terminal velocity Vt, and velocity is decreasing as you are moving in the direction, as we are moving towards the plane, right? So this is the velocity variation. This is the velocity variation, right? So simply we can write, beta, simply we can write that tau, because each layer experiences the same shear stress. So simply we can write tau is equal to, this is mu into Vt minus 0, right? Vt minus 0 divided by that gap. And what is that gap? What is the gap? That gap is h, right? So Vt minus 0 divided by h. So tau is equal to, this is mu Vt by h, right? This is the tau. And once you know the tau, can we calculate the shear force? Once you know the tau, can we calculate the shear force? Yes, definitely we can calculate the shear force. So shear force is equal to tau multiplied by A, right? Shear force is equal to shear stress multiplied by area, right? Which area? Area of the block A, which is in contact with the fluid or liquid, right? Now see, tau multiplied by A. So tau is mu Vt, right? Mu Vt divided by h multiplied by area is equal to m multiplied by g. So what is the terminal velocity? From this equation you can easily calculate the terminal velocity. So what is the terminal velocity? The terminal velocity is, this is the mgh divided by mu times of A, right? So this is the terminal velocity, right? This is the terminal velocity, right? This is the terminal velocity. Is it clear to everyone? Is it clear to everyone? Please type in a chat box. Is it clear to everyone? So this is the mathematical expression of terminal velocity. Fine. Now come to the next case. We discussed about application of Newton's law of viscosity. So I think we discussed 7 or 8 cases, right? 7 or 8 cases. So force required to pull the shaft with constant velocity v, that we discussed. Okay. Force required to pull the shaft with constant velocity v in a tapered sleeve, right? So let us consider a tapered sleeve. Let us consider tapered sleeve. So beta, this is the tapered sleeve. Okay, first draw the shaft. Now first draw the shaft. First draw the shaft. So this is the shaft. This is the shaft. I think this is your homework. Anyone try? Anyone tried this question? So this is the shaft, and this shaft having this shaft having dia, let us consider that is di, right? This shaft having dia, let us consider di. And what is the length? So length of this shaft, let us consider that is L, right? And this shaft is in tapered sleeve. So beta, this is the tapered sleeve, right? This is the tapered sleeve, right? This is the tapered sleeve. And to minimize the friction, to reduce the friction, lubricant is used, right? So this is the lubricant. This is the lubricant. This is the lubricant. right? And here this gap is h1, and here the gap is h2, right? And this is the force F, right? This is the force F. This is the force F, which is used to pull the shaft. And because of this force F, what is the velocity of this shaft? That velocity of the shaft is v, and that v is constant. So in this case, calculate F. In this case, calculate F. What is the force required? What is the force required to pull this shaft with constant velocity v? So anyone tried this question? Okay. Now in this case, beta, in this case, that h is not same, right? As let us consider this is x is equal to 0. Let us consider this is x is equal to 0. Let us consider. So as we are moving in the x direction, so h is continuously changing with respect to x, right? What is the h? That h is the gap. So if I'm talking about the shear stress, the tau from the Newton's law of viscosity, if I'm talking about the shear stress, so shear stress we can write that is mu du by dy, right? Shear stress at any layer is equal to mu du by dy at that layer, right? And if we are assuming the linear velocity profile, then we can say that tau at any y is equal to mu into this is v minus 0 divided by h. We can say like this, na? Right? That tau at any y is equal to, that is mu into v minus 0 divided by h. But in this problem, right, in this particular case, this h is a function of x. This h is a function of x. So how you calculate the shear force? How you calculate the force F which is required to pull the shaft in this particular case? So can anyone tell me? In the previous case, I think this is the case, right, where that h is constant, right? In this particular case, the force required to pull the shaft with constant velocity v in a sleeve. In this particular case, in a case number 7 that we already discussed in the previous class. So in case number 7, that h is constant, right? H is not changing with x, but in this particular problem, h is changing with respect to x. So if h is changing with respect to x, so shear stress also changing with respect to x. So if I'm talking about the shear stress here, 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 so that shear stress is not same. Shear stress also changing with respect to x. Why? Because h is changing with respect to x. So whenever you are getting such type of problem, right? Whenever you are getting such type of problem where the dependent variable, this is the dependent thing, that dependent thing is continuously changing, then in this case what you are doing? You are using the integration concept, right? You are using the integration concept. Not same concept, same integration concept we are using here, right? So first we are finding the shear stress for the small element, right? First we are finding the shear stress, or I can say first we are finding the shear force for the small element, right? Then we perform an integration, then we can calculate the total shear force, and that shear force is equal to that F only. Are you getting my point? Or not? So if you apply the equation of motion, right, if you apply the equation of motion, so summation, right, summation fx is equal to 0, or summation fx is equal to, simply we can write this is the m ax, right? Just 1 minute, no beta, just 1 minute. Okay, so see here, the summation Fx is equal to max, right? And acceleration is 0. Acceleration is 0 because this shaft is moving with constant velocity v. So acceleration is 0. So summation Fx is equal to summation Fx is equal to 0, and summation Fx equal to 0. So simply we can write beta this F is equal to Fs, right? That F is equal to Fs, right? The force which is required to pull the shaft is equal to shear force experienced by this shaft. Okay, now for the calculation of the shear force, what I'm doing here, I'm considering a very small element. See here, I'm considering a very small element. Let us consider this particular portion. So let us consider this dimension is dx. So at a distance x, I'm considering a small element, that is dx. So first calculate the shear force experienced by this small element, right? First calculate the shear force experienced by this small element, right? So small elemental shear force, first calculate small elemental shear force, right? So what is the small elemental shear force? We can write dfs is equal to, this is tau multiplied by, that is dA, right? What is the tau? Tau is the shear stress on this small element, and what is the dA? The dA is the small elemental area. Now tell me what is tau? What is tau? So from the Newton's law of viscosity, we can easily calculate the tau. And beta here also velocity variation is not mentioned, na? So if velocity variation is not mentioned, then no problem. Assume the velocity variation as linear, right? So this is the velocity variation. Right? This is the velocity variation. So calculate tau for this small elemental area, right? Calculate tau for this small elemental portion. So calculate tau from the Newton's law of viscosity, from Newton's law of viscosity. So simply we can say that tau is equal to beta, that is mu, right? The dynamic viscosity of the liquid is mu into, that is v minus 0 divided by h, right? So let us consider here, beta, here where you consider a small element, here this height or this gap, right? For this small element, that gap is h. For this small element, the gap is h. Are you getting my point? Right? Where you consider a small element, for that small element, right? For that small element, this gap is h. So that's why I'm writing h. Okay. So this is the shear stress experienced by this small elemental, or for this is the shear stress experienced by this small element. Is it clear or not? Okay, fine. Now, so we can write that dfs is equal to, this is mu v by h into, now tell me what is the dA, beta? What is the dA? Tell me what is the dA? Can anyone tell me what is the dA? What is the small elemental shear area? Can anyone tell me what is the dA? So beta, that dA is, we can write, right? This is the pi di into dx, right? Pi di into dx. So this is the, yes, very good. This is the, right, pi di into dx. So this is the small elemental area, or this is the small elemental shear area, right? So we can write this is pi di into dx, So this is the small elemental shear force. This is the shear force experienced by this small element, right? Mu v, right, h into pi di dx. but I want to calculate the total shear force. 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 So what is the total shear force? So it is simply integration of dfs, or we can write mu vh pi di into dx, pi di into dx, right? And what is the limit? What is the limit? Can anyone tell me what is the limit? What is the limit, beta? What is the limit? 0 to L na? What is the limit of x? That is 0 to L na? 0 to L. So what is the limit? The limit is 0 to L. What is the limit? The limit is 0 to L. This is the limit. Very good. Okay, now mu is constant, mu is not function of x. Mu is constant, right? Mu is constant. So take mu from outside, take mu from outside the integration. This is mu. H is a function of x. V is also not function of x. V is also not function of x. V is also not function of x. What is the velocity at the surface? What is the velocity at the surface? What is the velocity at the surface of the shaft? That is V. Here also V, here also V, here also V, here also V. So V is not function of x, right? V is not function of x. So V is not function of x. V is not function of x. Pi is constant. Di is also not function of x, right? 0 tends to L, and this is dx by h. Dx by h. H is a function of x. So mu not function of x, V not function of x, pi constant, di is not function of x. Right, fine. Now, can anyone tell me how h changes with respect to x? How this h changes with respect to x? How the h changes with respect to x? Can anyone tell me? So it is very much clear. H linearly changes with x. It is very much clear, beta. If you see this diagram, then it is very much clear that h linearly changes with x. Right? H is a linear function of x. H linearly varies with x. So we can write h is equal to a plus bx, because we know that h is not constant na? H changes with respect to x. If h changes with respect to x, and it is very much clear from this diagram, h linearly changes with respect to x. So how we can write h is equal to a plus bx, where a and b are constant. Where a and b are constant. Now, can we find out the value of a and b? Can we find out the value of a and b? Can we find out the value of a and b? Yes, we can find out the value of a and b. So beta, for this we need a boundary condition. For the calculation of a and b, we need boundary condition. And what are the boundary condition? Two boundary conditions are required, because we have two constants. So what are the boundary condition? The first boundary condition is at x is equal to 0, at x is equal to 0, h is equal to h1. And what is the second boundary condition? At x is equal to L, h is equal to h2. This is the second boundary condition. So if you apply the first boundary condition, x is equal to 0, h is equal to h1. So simply a is equal to h1. Now apply the second boundary condition, at x is equal to h is equal to h2. So h2, right, is equal to h1. That a value is h1 plus this is b multiplied by L. So from here we can say b is equal to, that is h2 minus h1, right? B is equal to h2 minus h1 divided by L. So this is b. So how h varies with respect to x? So put the value of a and b in this expression. So simply we can write h is equal to h1 plus h2 minus h1 L into x. So this is the variation of h with x, right? This is the variation of h with respect to x, right? Or simply we can say let k is equal to h2 minus h1 divided by L. Let k is equal to h2 minus h1 divided by L. So simply we can write h is equal to beta h1 plus k into x. Simply we can say that h is equal to h1 plus kx, where k is h2 minus h1 by L, right? Now come to this step, mu v pi di, right? 0 tends to L. Now dx and h, we can write this is h1 plus kx, right? And you know integration of this na, you know integration of this portion na, you know this integration na. I already discussed in the previous class. You know this integration na, integration of a plus bx. You know integration of a plus bx na. What is the integration? What is the integration of 1 upon a plus bx? What is the integration of 1 upon bx? What is the integration of this? So this is 1 upon b ln a plus bx. This is the integration of 1 upon a plus bx. Is it fine? Now, so if you perform integration, this is mu v pi di, right? And this is 1 upon k into ln h1 plus kx, right? And what is the limit? The limit is 0 to L. What is the limit? The limit is 0 to L, right? Now we can say that Fs is equal to, this is mu v pi di, right, divided by k into, right, this is ln h1 plus kl minus ln h1, right? If you perform the integration and if you putting the, right, if you putting the limits, then you are getting this one, right? So ultimately what you are getting, that Fs is equal to, this is mu v pi di divided by k into, right, k is h2 minus h1 by L na. This is ln and this is ln h1 plus k, h2 minus h1 by L. So L is cancel out. So it comes h2 minus h1 minus ln h1, right? And finally what you are getting, Fs is equal to, the shear force is equal to mu v pi di k, mu v pi di k, right? And h1 cancel out. So ln h2 minus ln h1. This is ln h2 minus ln h1, right? Now put the value of k also here. So this is mu v pi di divided by h2 minus h1 into L into ln h2 by h1. So simply we can write, beta, this is mu v pi di L divided by this is h2 minus h1 divided by ln h2 by h1. This is the shear force. This is the shear force experienced by this shaft, or this is the force which is required to pull the shaft. And where this term, right, h2 minus h1 divided by ln h2 by h1, this is equal to hm. And what is this hm? This is nothing but the logarithmic mean. This is the logarithmic mean. Beta, this is nothing but the logarithmic mean of h1 and h2 na. This is the logarithmic mean of h1 and h2 na. We know about the arithmetic mean, we know about the geometric mean, right? In a similar fashion, this is the logarithmic mean, right? Logarithmic mean of h1 and h2. So hm, right, this h2 minus h1 upon ln h2 by h1, this is nothing but the hm, and this is the logarithmic mean of h1 and h2. Logarithmic mean of h1 and h2. So simply we can write, this is equal to mu v pi dil divided by hm, right? So ultimately this is your shear force, right? This is your shear force, mu V divided by HM, right? This is the shear stress multiplied by shear area. So this is the pi DIL. But this is the shear force. This is the shear force, and this is also equal to force which is required to pull the shaft. Is it clear to everyone? Tell me, is it clear to everyone? Is it clear to everyone? Okay, so whenever you are getting related to problem with a tapered shaft, whenever you are getting a problem related to the tapered sleeve, and that tapered sleeve, right, that tapered sleeve, or we can say that H variation with respect to X is linear, right? Whenever you are getting such type of problem where sleeve is tapered, right, sleeve is tapered and H varies with respect to X as a linear, right? So you can directly remember this, better see, if there is a shaft, and that shaft is in a sleeve where H is not function of X, like this, in this case, right? In this case, this is the shaft, and this shaft is in a sleeve, this shaft is in a sleeve, this is the sleeve, and to reduce the friction there is a lubricant, right? And this is the force F which is required to pull this shaft with constant velocity V. So in this case, what is the F? So simply we can write beta F is equal to, this is tau multiplied by area, shear area. And what is the tau? From the Newton's law of viscosity, simply you can say this is mu into, this is delta U by delta Y into, what is the area? What is the shear area? Right? The shear area is simply, you can write this is pi di into L, where di is the this dia, and this is the length of the shaft, right? And what is the delta U by delta Y? This is mu multiplied by V minus 0 divided by this is the gap, which is H into, this is pi di into L, right? And what is the H? So simply we can write that H is equal to beta, this is the R naught minus Ri. Sir, what is the R naught? So this is the R naught, this is the R naught, and this is the Ri. This is the Ri. Is it fine? Right. So this is the case where H is not function of X, but this is the case where H is a function of X. And how H changes with respect to X, that is a linear variation. So in this case, what you are getting, similar kind of expression. The only difference is, instead of H, use HM, right? Instead of H, use HM. And what is that HM? That HM is logarithmic mean of H1 and H2. So simply you can write H2 minus H1 upon natural log H2 by H1. Is it fine? Is it clear to everyone? This case is clear to everyone or not? Tell me fast. Beta, this case is clear or not? Tell me. This case is clear or not? Tell me. So this is the case number 8. This is the case number 8. Is it clear to everyone? Is it clear to everyone? Okay. Now come to the case number 9. Right? Case number 9. See, from every case you are getting a question. Right? From every case you are getting a question. So this is the case number 9. This is the case number 9. Power required to rotate the shaft in a sleeve with constant angular velocity omega. So let us consider there is a shaft. So this is the shaft, right? This is the shaft. Right? And let us consider the diameter of the shaft as di, right? and this shaft is in a sleeve. So this is the sleeve, right? This is the sleeve. This is the sleeve. And to reduce the friction, lubricant is used. So this is the lubricant. This is the lubricant. Right? This is the lubricant. Fine. And let us consider that outer dia, this dia is D naught. Okay. And this is the H. So can anyone tell me what is the H? This is the gap H. So beta, this gap H is nothing but the radial clearance, right? This H is nothing but the radial clearance. I think I already discussed about the diametral clearance and the radial clearance now. What is the diametral clearance? 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 So diametral clearance is D naught minus Di. This is the diametral clearance, right? This is the diametral clearance. And what is the radial clearance? What is the radial clearance? That radial clearance is R naught minus Ri. So here H is nothing but the R naught minus Ri, or you can say D naught minus Di by 2. Fine. Now in this question, this is the central axis of the shaft. In this question, in this particular case, power is asked, right? Power required to rotate the shaft in a sleeve with constant angular velocity omega, right? So this shaft is rotating with constant angular velocity omega. So what is the power required for that? What is the power required for that? Right? This is the question. Right? Power required to rotate the shaft with constant angular velocity omega. With constant angular velocity omega. This is the question. So beta, how you calculate the power? Remember now, what is the power? That power is equal to, we can write this is torque multiplied by angular velocity omega, right? Power is equal to torque multiplied by omega, or simply you can write this is 2 pi nt by 60, right? 2 pi nt by 60, where omega is the angular velocity, in radian per second, na? In radian per second. What is the n? That n is the RPM, right? What is the n? That n is the RPM. What is T? T is the torque, right? What is the T? T is the torque. So you can find out the power. By using this mathematical expression or using this mathematical expression. Fine. So before calculating the power, first calculate the torque. So how you calculate the torque? What is the torque required to rotate this shaft with constant angular velocity omega? This is also called frictional torque, right? This is also called frictional torque, or you can say torque required to overcome the friction, or you can say torque required to rotate the shaft with constant angular velocity omega, right? So I want to calculate this torque. So how you calculate this torque? Tell me how you calculate this torque. So beta, this torque is simply shear force experienced. Torque is nothing but the torque is a kind of moment, na beta. Torque is a kind of moment, you know very well. And if I'm talking about the moment, so moment is nothing but the force multiplied by perpendicular distance. No, it is not 16t by pi dq. No, beta, it is not 16t by pi dq. Right? What is the basic definition of definition of moment? Right? What is the basic definition of the moment? So the moment is nothing but the force multiplied by the distance. In this particular case, force multiplied by radial distance. So we can say this is Fs multiplied by Ri. Right? Fs multiplied by Ri. Yes, very good, very good. So we can write now, in this way now, force multiplied by, what is the force? The force is the shear force, because, or shear force you can say, or viscous force you can say. Right? Shear force is nothing but the beta viscous force, resistance force. I already told you multiple times. Right? Shear force, right? You can say resistance force, you can say friction force, you can say viscous force. That is same. Right? So viscous force or shear force multiplied by the radial distance, and that is nothing but the Ri. So this is the torque which is required to rotate this shaft. Is it fine? And you know very well how to calculate this Fs. You know very well how to calculate this Fs. Sir, how Fs will generate? Okay, how Fs will generate? Because see, the shaft is trying to rotate, na? Shaft is trying to rotate. So what about this lubricant? Right? But if you see the cross section of the shaft, let us consider this is the cross section of the shaft. This is the cross section of the shaft. Right? This is the cross section of the shaft. And outside this shaft there is a lubricant, na? Outside this shaft there is a lubricant. Right? And this shaft is, let us consider this shaft is trying to rotate in a clockwise direction with angular velocity omega. This shaft is trying to rotate in a clockwise direction. Right? So definitely between the surface of the shaft and the lubricant. Just 1 minute, na? Just one minute. I think I'm not able to see your comment. Just 1 minute. Okay. Now see, if I'm talking about this shaft is trying to rotate in a clockwise direction. So beta, what about the resistance force? And that resistance force, because of this lubricant, the resistance force is acting in the opposite direction, na? Resistance force is acting in the opposite direction, na? Resistance force is acting in the opposite direction, na? Tell me yes or no. So beta, this is the resistance force. This is the resistance force, and this is nothing but the Fs. So in this manner, the shear force or viscous force or resistance force come into picture. Is it fine? Okay. Now, how you calculate this Fs? How you calculate this Fs? From the concept of fluid mechanics, how you calculate this Fs? So we have the Newton's law of viscosity now. Right? We have very, very important tool, that is the Newton's law of viscosity that we have. And from the Newton's law of viscosity, we can write from Newton's law of viscosity, we can write shear stress experienced by any fluid layer is equal to mu du by dy. And once you know the shear stress, then we can easily calculate the shear force. Once you know the shear stress, then we can easily calculate the shear force. Fine. So can you see again, in this lubricant the velocity profile is not mentioned. So beta, no problem, assume linear velocity profile. Assume linear velocity profile. Assume linear velocity profile in the lubricant. So this is the velocity profile. Right? This is the velocity profile. Right? This is the velocity profile. Okay, so angular velocity we know that is omega. So there is any relation between the angular velocity and the linear velocity, right? There is any relation between the angular velocity and the linear velocity. If I say, let us consider at the surface of the shaft, the linear velocity is v. Linear velocity is v. At the surface of the shaft, the linear velocity is v. The angular velocity is omega. Linear velocity is v. So can anyone tell me what is the relation between the linear velocity and the angular velocity? So beta, everyone knows that v is equal to, we can write omega times of ri, right? V is equal to omega times of ri, where ri is the radius of the shaft. So this is the tangential velocity, you can say, or you can say linear velocity. Omega is the angular velocity, right? V is the linear velocity. Linear velocity, what is the unit? Unit is meter per second. Fine. Okay. So can you calculate the shear stress? Can you calculate the shear stress? Yes, we can easily calculate the shear stress. So shear stress is equal to, this is mu into, this is delta u by delta y, right? And this is mu into, what is the delta u? That is v minus 0. V minus 0 divided by, v minus 0 divided by, what is the gap? That gap is h. That gap is h. Right? So it is very much clear, beta, this shear stress is not function of x, or not function of the length, mu v by h. Right? From this mathematical expression, it is very much clear this tau is not function of the length of the shaft. Right? That means here also, right, here, just 1 minute now, here shear stress is, say, here shear stress, here shear stress, shear stress, shear stress, shear stress, that is same. Shear stress is not function of the length of the shaft. Is it fine? Now calculate the shear force. So this is the shear stress. Now calculate the shear force. Calculate the shear force or viscous force or resistance force. So shear force is equal to, this is tau multiplied by shear area. Tau multiplied by shear area. So can anyone tell me what is the shear area? Can anyone tell me what is the shear area? Can anyone tell me what is the shear area? So beta, shear area is nothing but the, see, this is pi into di, and perpendicular to the monitor there is a length which is L. So this is the shear area. This is the area where shear stress act, not pi r square. Pi r square is a cross sectional area, beta. Pi r square is the cross sectional area. Shear stress is not acting in a cross sectional area. Shear stress is acting in a surface area. Right? Shear stress is acting in a surface area. So let us consider, if this is a shaft, right? So if, let us consider this is try to rotate in a clockwise direction. So shear stress is acting in a opposite or shear stress is acting in a anti-clockwise direction. Is it fine? And that shear stress acting in a surface area, because surface area is in contact with the fluid. Is it clear to Sahib? Is it clear to you or not? Right? So tau multiplied by what is the shear area? The shear area is pi DIL. So beta, whenever you calculate the shear force, this area is nothing but the shear area, na? This area is nothing but the shear area, or you can say area where shear stress is acting, or you can say in very simple manner, the area of an object which is in contact with the fluid. Simple, right? Area of a object or area of a body which is in contact with the fluid. Simple, right? So A is nothing but the shear area, right? So Fs is tau multiplied by pi di into L. Fine. And what is the tau? The tau is mu v h into pi DIL, right? And once you know the shear force, then you can calculate the torque. Torque you can say, or viscous torque you can say. viscous torque, or you can say torque which is required to rotate the shaft. So torque is Fs multiplied by di by 2, right? Ri, so Ri is di by 2. So we can write this is mu v L pi di square divided by 2 times of h. So this is the viscous torque. Now what is the power? Now tell me what is the power? Now tell me what is the power? What is the power? What is the power required to rotate the shaft? So this is T multiplied by omega. So that is T now. That means mu VL, right? Mu VL pi di square, right? Mu VL pi di square 2h into omega, right? Or we can write in another way also omega. Omega is V multiplied by, right? Power is equal to power required to rotate the shaft, that is equal to mu VL. This is T multiplied by omega. So this is mu VL upon, right? Mu VL upon 2h pi di square multiplied by omega. And what is the omega? That omega is, right? What is the omega? So simply we can write V is equal to omega V is equal to omega Ri. So omega is V by Ri, right? V by Ri, or we can say di by 2, right? So 2 and 2 is cancel out. Di and di is cancel out. So ultimately what you are getting, mu VL by h into this is pi di, right? This is the power which is required to rotate the shaft, right? So there is no need to remember this expression now. There is no need to remember this expression. There is no need to remember this expression. You just learn the concept, and once concept is clear, then definitely you are able to solve the problem, right? Once concept is clear, then you can able to solve the problem. Okay, so let's try one problem. So this is the concept. Now try to solve this problem, right? Try to solve this problem. This is the NAT problem. So try to solve this problem. Try to solve this problem. Okay, so from tomorrow your class timing is 8:30 to 10 na? From tomorrow onwards your class timing is 8:30 to 10 p.m. right? So from tomorrow onwards this is the class timing, 8:30 to 10. Okay, so in this problem there is a cylindrical shaft, right? In this problem there is a cylindrical shaft, and that cylindrical shaft having dia which is 90 millimeter, rotated about a vertical axis inside a fixed cylindrical tube of diameter 95 millimeter and length is 50 centimeter. Fine. The rotational speed of the shaft is 240 rpm. Fine. So rpm of the shaft is mentioned, that is 240 rpm. If the space between the shaft and tube is filled by a lubricant having viscosity 2 poise, then what is the power required to rotate the cylindrical shaft in watt? Right. So there is a cylindrical shaft. There is a cylindrical shaft. So let us consider this is a cylindrical shaft. Right. This is the cylindrical shaft. Right. And what is the diameter of this cylindrical shaft? The diameter is 90 mm. Right. The diameter is 90 mm. And this shaft is in the vertical tube. So let us consider this is the vertical tube inside a fixed vertical tube. So this is the vertical tube, right? And this vertical tube is fixed, right? And the diameter of this vertical tube is mentioned, and that is 95 millimeter. 95 millimeter. So this is the diameter, right? This is the diameter, 95 millimeters. So this is the diameter of the tube. Fine. And to minimize the friction, to reduce the friction, there is a lubricant. So this is the lubricant, right? This is the lubricant. Right? This is the lubricant. And what is the viscosity of this lubricant? That is 2 poise. That is 2 poise. So this is the viscosity of the lubricant, and this shaft is rotated, right? This shaft is rotated about vertical axis. So let us consider this is the axis, and about this shaft is rotating. Shaft is rotating with rpm. So n is mentioned, that is 240 rpm. That is 240 rpm. So in question, power required to rotate the cylindrical shaft, that is asked. So power required to rotate the shaft, right? So you can calculate power required by rotate the shaft by using this concept, right? T multiplied by omega. This is better, T multiplied by omega, or 2 pi nt by 60, or simply shear force multiplied by the velocity of the shaft, tangential velocity or linear velocity of the shaft. So Fs multiplied by V, right? You can calculate the power required to rotate the shaft by using T into omega, or 2 pi nt by 60, or Fs multiplied by velocity of the shaft. Which velocity? Tangential velocity or linear velocity. Fine. Now first calculate beta shear force. Whenever either you are using this or this or this, anyways, first Fs is required, right? First Fs is required. So what is the Fs? The shear force. Shear force acting on the surface of the shaft. Shear force acting on a surface of the shaft. Shear force acting on a surface of the shaft, right? So this is simply, we can write tau multiplied by area. Which area? Shear area. And shear area means area which is in contact with the fluid or lubricant, right? And beta, this length is also mentioned. Na? This length is also mentioned. I think this is 50 centimeter. This is 50 centimeter. This is 50 centimeter. Right. So Fs is nothing but the tau multiplied by area. Which area? Shear area, or area of the shaft which is in contact with the fluid. Right. Now again see, to calculate the tau, right? We have a very, very important tool, which is the Newton's law of viscosity. And to apply the Newton's law of viscosity, you must know the velocity variation in this fluid, in this lubricant. How velocity, how layer to layer velocity changes. You must know this, right? So whenever velocity profile is not mentioned in the problem, then there is only one solution. Assume that velocity profile as a linear, right? And at the shaft axis, what is the velocity? At the shaft axis, at the shaft surface, I'm sorry, at the shaft surface, what is the velocity? That velocity is equal to v, right? That is the tangential velocity of the shaft. That is the tangential velocity of the shaft. Fine. Now, can we calculate the tangential velocity of the shaft? Yes, we can calculate. So v is equal to, this is omega multiplied by ri. And omega, what is the omega? That is a 2 pi n by 60, na? 2 pi n by 60, because n is given in rpm. So to convert n in rps, we are dividing with 60. So 2 pi n by 60 into ri. So first calculate v, that is the tangential velocity of the shaft surface. So beta, this is 2 pi multiplied by, that n value is given 240, into what is the radius of the shaft? What is the radius of the shaft? The diameter is 90 millimeters. So what is the radius? That is 45 millimeter. So this is 45 into 10 to the power minus 3 divided by 60. So tell me what is the tangential velocity of the shaft surface. So tell me what is the v? Tell me what is the v? Can anyone tell me? 1.130. Everyone getting the same answer? 2 pi multiplied by 240 into 45. 2 pi into 240 into 45 into 10 to the power minus 3 divided by 60. So it comes 1.131 meter per second, right? This is the tangential velocity at the shaft surface, 1.130 meter per second. Fine. Now we can use the Newton's law of viscosity. So from Newton's law of viscosity, we can write tau. Tau as, this is mu multiplied by delta u by delta y into a, right? So mu multiplied by, what is the delta u? What is the delta u? What is the velocity? What is the, this is a linear velocity profile, na? So simply we can write v minus 0. This is v minus 0. And what about the gap? Beta, what about the gap? This is the gap. This is the h, right? This is the h. This is the h. This is the gap, h. So can anyone tell me what is the h? So this h is nothing but the, this h is nothing but the r naught minus ri, na? That h is nothing but the r naught minus ri, na? R naught minus ri, na? H is nothing but the r naught minus ri, na? And what is the r naught? That r naught is 95 by 2. R naught is 95 by 2 minus, what is the ri? That is 90 by 2. 90 by 2. So calculate h. What is the h you are getting? 95 by 2 minus 90 by 2. Right? 95 minus 90. So 95 minus 90. Right? 95 minus 90, that is 5. So this one is 5 by 2. That means 2.5. So h is 2.5 millimeter. H is 2.5 millimeter. H is 2.5 millimeter. Right? So simply we can write h here into, what is the area? What is the area? That is the shear area. Right? What is the area? That area is a shear area. So shear area is, this is 2 pi ri multiplied by L. Right? 2 pi ri multiplied by L. So you can calculate Fs from here. So Fs is equal to, the shear force is equal to, right? What is mu? Mu is 2 poise. So 2 poise, that means 0.2 Newton second per meter square. 0.2 multiplied by, right? V minus 0. What is V? 1.131. 1.131 divided by, what is the h? That h is 2.5 mm. So this is 2.5 into 10 to the power minus 3 into 2 pi ri into 2 pi, what is the ri? That ri is 45 millimeter. 45 millimeter. So 45 millimeter That means 45 into 10 to the power minus 3. Right, so 2 pi Ri into L. L is 50 centimeter. So this is 50 multiplied by 10 to the power minus 2. Right, so 10 to the power minus 3, 10 to the power minus 3 is cancel out. So calculate shear force from here. Right, calculate shear force. Tell me what is the shear force? Tell me what is the shear force? Tell me what is the shear force? What is the shear force? So 0.2 multiplied by 1.131 into 2 pi into 45 into, right, 0.2 1.131 2 pi 45 into, this is 0.5 divided by 2.5. I think this comes 12.7. Right, please check the calculation. It comes 12.791. 12.791. Everyone getting the same answer? Fs, shear force. Everyone getting the same answer? 12.791 or simply 12.88 Newton. Right, so this is a shear force. Now, we need power, na? Power. Power required. Power required to rotate the shaft. To rotate the shaft. This is also called frictional power. Right, or power required to overcome the friction. Power required to rotate the shaft. So simply we can write shear force multiplied by velocity of the shaft. Shear force multiplied by velocity of the shaft. So shear force is 12.791 into velocity. That velocity of the shaft is 240 rpm, na? 240 rpm, or no, 1.131 meter per second. Tangential velocity is required, na? 1.131, and this comes in watt. So tell me what is the power? Tell me what is the power? So this is 12.791 into 1.131. 12.791 into 1.131. So this comes 14.466 watts. So this is the power required to rotate the shaft. This is the power required to rotate the shaft. 14.46. This is the power required to rotate the shaft. Is it clear? Is it clear or not? Is it clear to everyone? Is it clear to everyone? Is it clear to everyone? Tell me. Shall we directly take? I'm not getting your question. What is your question? Clear, na? Okay. Any doubt, Praveen Raj? Praveen, any doubt? Actually, I'm not getting your question. Okay. Now come to the last case. Case number 10. Power required to rotate the disc over a fixed plate with constant angular velocity omega. Right? Power required to rotate the disc over a fixed plate with constant angular velocity omega. So this case, for this case, we can solve one problem. This is a problem. Right? This is nothing but the case number 10 only, right? This is nothing but the case number 10 only. Right? Case number 10 in form of problem. Right? Case number 10 in form of problem, in terms of problem. Case number 10. Right? Case number 10. Case number 10 in form of problem. Right? So beta, this is the MCQ problem. Okay. Now read the question carefully. Read the question carefully. A circular disc of radius capital R is kept at a small height h, right? A circular disc of radius R is kept at a small height h above a fixed bed by means of a layer of oil of dynamic viscosity mu. Power required to rotate the disc with constant angular velocity omega is, assume linear velocity profile within the oil film, right? And you have four option. You have four option. Fine. Now, see. So let us consider there is a disc. Let us consider there is a disc. Right? Let us consider there is a disc. And this disc is above the bed or above the fixed plate. So this is the fixed plate. Right? This is the fixed plate. And this disc is rotate about this axis, right, with constant angular velocity omega. With constant angular velocity omega. And what is the radius of the disc? So let us consider radius of the disc is capital R. It is also mentioned in the problem, right? Circular disc having radius that is capital R. And to reduce the friction between the, right, this is the bed, na? This is the bed. This is the bed, right? Bed is nothing but the fixed plate only. This is the fixed plate. And this is the disc. This is the circular disc, right? This is the circular disc. And to minimize the friction, to reduce the friction between the bed and the disc, lubricant is used, right? So this is the lubricant, right? And this height or this gap is mentioned as h now. That height is h. This is the h. This is the h. Now in this question, right, in this question, what is asked? What is the power required to rotate? What is power required to rotate the disc? So power required to rotate the disc, we know beta. Power required to rotate the disc. Power required. Power required to rotate. Power required to rotate the disc. Power required to rotate the disc. Simply we can say this is the power required to rotate the disc. Simply we can say T multiplied by omega, or we can say this is a tau. We can say 2 pi nt by 60, or we can say shear force multiplied by velocity of the disc. Right? We can say like this. But see here. In this case, what is the problem actually? In this case, what is the problem? Right? I will tell you the problem. Beta, if you see velocity here, right? If you see velocity here, which velocity? The tangential velocity. Right? Which velocity? Tangential velocity. So if you see velocity here, that is omega multiplied by r, right? Or omega multiplied by r1. Let us consider this point is at a radial distance r1 from the axis, right? So what is the tangential velocity here? That is the omega into r1. What is the tangential velocity here? That is the omega into r2. What is the tangential velocity here? That is the omega into r3. What is the tangential velocity here? That is omega into r4. So if you write the Newton's law of viscosity, what is the Newton's law of viscosity? That tau at any y is equal to mu, that is du by dy. And if there is a linear velocity variation, so we can write mu multiplied by v minus 0, so v divided by h. So beta, in this case, v is a function of r. Are you getting my point? In this case, this v is a function of r. right? As you are moving in this direction, as you are moving in the radial direction, that tangential velocity changes with respect to r. The tangential velocity changes with respect to r. Are you getting my point or not? That means if you see the top view of this disk, let us consider this is the top view of the disk. Let us consider, right? This is the top view of the disk. Okay, right? This is the center. This is the radius capital R. Sorry, this is the radius capital R. This is the radius capital R. That means at this layer shear stress is different. At this layer shear stress is different, right? At this radial distance shear stress is different. At this radial distance shear stress is different. Are you getting my point? Right? At this particular radial location, at this particular radial distance, shear stress is different. Here shear stress is different. Here shear stress is different. Here shear stress is different. Why it is different? Because V is a function of R. So since V changes with respect to R, therefore the shear stress also changing with respect to R. Is it fine? Is it okay? Is it clear or not? Tell me, guys. Is it clear or not? Is it clear or not? Tell me. Is it clear or not? Tell me. Okay, so shear stress is changing with respect to R. So definitely shear force is also changing with respect to R. And there is a need to calculate the total shear force. There is need to calculate the total shear force. So how you calculate the total shear force? How you calculate the total shear force? So beta, first find out the small elemental shear force. First find out the small elemental shear force, and once you know the small elemental shear force, then perform integration. Are you getting my point? Why integration is performed here? Why integration is performed here? Because in this particular case the shear stress is not constant. Shear stress is changing with respect to R, and hence shear force is also changing with respect to R. So first we calculate the small elemental shear force, and once small shear force is calculated, then find out the total shear force by using the integration constant. Is it fine? Or first calculate the small elemental torque, or first calculate the small elemental torque and perform the total integration, and once total integration is performed, once total torque is calculated, right, then you can find out the power. Okay, so first calculate the small elemental shear force. To calculate small elemental shear force, what I am doing here, at a radial distance r, I am considering a small elemental area. At a radial distance r, I am considering a small elemental area. So this is the small elemental area. Right, this is a small elemental area. And what is the thickness of this small elemental area? What is the thickness of this small elemental area? So that thickness is dr, right? That thickness is dr. Okay, so calculate a small elemental shear force. First calculate a small elemental shear. First calculate a small elemental shear force. So what is the small elemental shear force? That is dfs, right? So I am considering element at a radial distance r. I am considering element at a radial distance r. And if you see here, so this is the radial distance r. This is the radial distance r. Right, and what is the velocity variation? That velocity variation is linear only, right? Velocity variation is linear only. So simply we can write better dfs is tau multiplied by a small elemental area, that is dA. Right, a small elemental area, that is dA. So calculate tau first. What is the shear stress experienced by this small element? So it is simple, already written here. Already written here from the Newton's law of viscosity. It is mu v by h multiplied by mu v multiplied by h is into, what is the dA? Can anyone tell me what is the dA? Can anyone tell me what is the dA? Can anyone tell me what is the dA? What is the dA? Can anyone tell me? Can anyone tell me what is the dA? What is the dA? Can anyone tell me what is the dA? So dA is nothing but the 2 pi r into dr. The dA is nothing but the, beta, this is 2 pi r into dr. This is the shear area, na? This area, this red shaded area, the red shaded area. So the red shaded area is nothing but the 2 pi r dr. Right? If anyone having doubt, then it is simple, na beta, that dA is equal to, you can calculate in this way also. Right? You can calculate in this way also, right? This shaded area, so this is the pi r plus dr square minus pi r square. You can calculate in this way also. What is the dA? The dA is, right, do one thing, right, do one thing, this minus, see, this, first calculate this, so that is nothing but the pi r plus dr square, pi r plus dr square. First calculate this, right, then subtract this portion only, this portion, then subtract this portion, pi r square, then subtract this portion, pi r square. Right, so pi r plus dr square minus pi r square. So from here what you are getting? From here what you are getting? You are getting this only. That is 2 pi r dr. Right, if you open this r plus dr ka whole square, so r square plus dr square, so dr is already a very small quantity, na? So dr square is also very, very small. Dr is a small quantity, so dr square is very, very small. Right, so if you open this r square plus dr square, so dr square is negligible, plus 2 pi r dr. So pi r square is cancelled out, so ultimately what you are getting? 2 pi r dr. Right, so this is the shear area. This is the 2 pi r dr. Right, so this is the small elemental shear force. Now calculate small elemental, or you can write omega into r. So mu into, right, omega into r divided by h, right, into 2 pi r dr, right, or you can write this is 2 pi mu omega by h into 2 pi mu omega by h into r square dr. Beta, this is the dfs. This is the small elemental shear force. This is a small elemental shear force. This is the small elemental shear force. Now calculate small elemental torque, or shear torque you can say, or viscous torque you can say. Small elemental viscous torque. Small elemental viscous torque. Small elemental viscous torque. Right. So what is the small elemental viscous torque? So this is the dfs multiplied by r. This is nothing but the dt. This is nothing but the dt. This is the small elemental viscous torque. Right, so dfs multiplied by r. Now tell me what is the dt, what is the small elemental torque? So this is dfs multiplied by r. So what is the dfs? What is the dfs? The dfs is 2 pi mu omega. This is 2 pi mu omega by h, right? 2 pi mu omega by h, r square dr. So r is also here, so this is r cube dr. Right. So this is the small elemental viscous torque. This is the small elemental viscous torque. Right. Now calculate total torque. Now calculate total torque. So calculate total torque. Total viscous torque. Calculate total viscous torque. So calculate total viscous torque. So this is the integration of dt, and this is integration of 2 pi mu omega h, 2 pi mu omega h into r cube dr. And what is the limit? The limit is 0 tends to r. Right? This is the limit. Right? So viscous torque is equal to, this is 2 pi is constant, mu is constant, omega is constant. Right? H is constant, variable is r. So if you perform integration, what you are getting? R to the power 4 by 4. Limit 0 tends to r. So ultimately what you are getting? This is 2 pi mu omega by h into r to the power 4 by 4. R to the power 4 by 4. So 2 2s are. So ultimately what you are getting? This is pi mu omega r to the power 4 by 2h. Right? This is the viscous torque. This is the viscous torque. And once you know the viscous torque, then you can easily calculate the power. Power required. Power required to rotate the shaft or disc. In this case, disc is present. Power required to rotate the disc. Right? This is T multiplied by omega. And this is T pi mu omega. Right? So this comes omega square r to the power 4 by 2h. So this is the viscous torque. This is the viscous power, or you can say this is the power required to rotate the disc. Right? Pi mu omega square r to the power 4 by 2h. Pi mu omega r square r to the power 4 by 2h. So this is the correct answer. This is the correct answer. This is the correct answer. Is it okay? Is it clear? Is it clear? Is it clear to everyone? Is it clear to everyone? Any doubt? Any doubt, beta? Any doubt? Any doubt related to this? Any doubt related to this? Any doubt related to this? Is it clear to everyone? Okay, fine. So I hope whatever the concept we discussed in today's class, that is clear to everyone. Okay. So in tomorrow's class, we will discuss another fluid properties. Right? In tomorrow's class, we will discuss another fluid properties like compressibility, bulk modulus. Right? Also, we will discuss about the capillarity concept, right? Surface tension concept, right? Vapor pressure concept, right? So that we will discuss in upcoming classes, right? And also we will discuss about the non-Newtonian fluids, right? So far our focus is on Newtonian fluids, right? But in upcoming lectures we will discuss about non-Newtonian fluids also. Right? So I hope whatever we discussed in today's class and also in the previous classes, that is clear to everyone. So beta, if you have any doubt, right? If you have any doubt, you can connect with me by Telegram channel. You know my Telegram channel, na? You know my Telegram channel, na? You know my Telegram channel? If you don't know, search by using this Sandeep Sir PW. Right? Sandeep Sir PW. So join Telegram channel, and whatever the doubt you have, you can ask in that channel also. Okay. Okay. So tomorrow's class timing is 8:30 to 10. Right? Tomorrow's class timing, from tomorrow onwards, class timing will be from 8:30 to 10 p.m. 8:30 p.m. to 10 p.m. Okay, so thank you so much guys. Bye bye, take care, and good night everyone. Good night.